hello everyone. So I'm a PhD student with Olivier, Schwander, Frédéric, Barbaresco, some of which are here, and Jean-Yves, Schneider and Matthieu at Thales, and the Laboratoire d'Informatique de Paris 6 at Jussieu in Paris. And we will be addressing second-order neural networks. So first, a brief context and introduction. So we're given two different fields. On the one hand, machine learning. On the other hand, information geometry. And in the past few years, it's been a quite successful trend to try to mix the both of them. So in a variety of different unrelated fields, such as radar data, EEG, ECG in the BCI context. So brain-computer interface. Also in video classification for emotion analysis or motion capture skeletal data. And other medical imagery fields such as MRI and DTI. So this is the context of this work, and more specifically, we'll be dealing with data which can be naturally interpreted as the realization of a Gaussian process. So this is a quite standard assumption in many signal processing fields. And on the machine learning point of view, we'll be also following a fashionable trend of deep learning. So specifically, we want to build, develop, and integrate in some popular deep learning frameworks neural networks adapted for basically covariance matrices, which have a symmetric positive definite structure, SPD. So we're trying to build SPD neural networks. So actually, this has already been done, so we're quite lucky. In 2017, the first SPD neural network was proposed, and the first part, or the second part of this presentation is dedicated to describing it. So, how does an SPD neural network work? So, similarly to a classical multi-layer perceptron, so the most basic form of neural network around, the aim of an SPD network is to build, given an input manifold, an output feature manifold, which is more compact, but more critically, which is more discriminative. So the matrices here are more separable. And we do so by learning a hierarchy of layers, of functions. So to do so, the original authors propose three main layers. The first one is this one. So it's a bilinear mapping layer. So its equivalent in classical Euclidean neural net is the linear or dense layer. So here we have the input matrix X, and the output is P. And the output P is obtained by a bilinear transformation by the weight matrix W. So the first subtlety here, or difference compared to Euclidean neural nets, is that we require P to also be SPD. And to do this, we have to constrain the matrix weight W to be full rank. Actually, we also constrain it to be in a compact space. So in practice, we constrain W to be a matrix of orthogonal weights. So basically, W belongs to a Stiefel manifold. So we have to deal with this during the training, and we'll talk about this later. The second main layer is the rectified eigenvalues. So the equivalent in a Euclidean net here is the rectified linear unit. And this layer doesn't act on the coefficients on the matrix, but rather on its eigenvalues. So that's another key difference with a traditional network. And we will have to deal with the backpropagation of gradients through an eigenvalue decomposition during the training, which we'll see again later. And the third main layer, which this one doesn't have a counterpart in the Euclidean world, it's the log eigenvalues layer. So what's the goal of this layer? It's to map the final output feature manifold to the left to a Euclidean space. And the reason we do this is because we don't know yet how to actually do the classification in the manifold. So by this I mean that I don't know how to do this, so if anyone has suggestions, I'm very open to hearing them. So basically we want to transform the final output manifold to a Euclidean space, and in this Euclidean space we're able to draw lines and do the classification. So basically the formula is a simple eigenvalue decomposition, and you take the log. This stems from the framework of log Euclidean geometry, and it basically amounts to projecting the matrices into the tangent plane of the manifold at the identity point. Okay, so now we know how to build a basic SPD neural network. We have 3 main layers, and we're able to do the inference. So this part we will actually skip and come back to later if we have some time, maybe, but I don't think we will. So now we go on to the learning. So how do we learn an SPD net? How do we backpropagate through this network? So we recall the 2 technical challenges. So the first one was the backpropagation through structured matrix functions. By this I mean nonlinear functions on the eigenvalues of a matrix and not the coefficients of this matrix. The problem is here that the classical chain rule, which is the backbone of the backpropagation algorithm, doesn't hold anymore in this Riemannian setting. And the second problem was the optimization constrained to a manifold. So if you remember, the bilinear mapping layer had Stiefel weights, basically. And in the part that we just skipped, there was also another layer which had a weight matrix constrained to the SPD manifold also. So to tackle the first problem, we're quite lucky, smarter people than me have generalized the notion of the chain rule to a Riemannian setting. So that's a nice formula which we can skip. So we recall that our structured matrix functions take this form. So we have an input matrix P. We do an eigenvalue decomposition, and we have a nonlinear function f on the eigenvalues sigma. And here's the formula for backpropagation. So during the backprop, we go from the output to the input. So the input is dx, the gradient of x with respect to the loss function of the network. And our output is dp, gradient of p. And the formula for this chain rule involves, so U, the eigenspace of P, and dx, of course, and the matrix L, which is called the Loevner matrix, or matrix of finite differences, which involves function f and its derivatives, basically. So this solves our first problem, so that's very good. And as for the second one, optimization with manifold constraints. So I'm sure I'm pretty redundant with what has already been said in previous lectures, but there's a drawing. So the backpropagation gives us a Euclidean gradient here, dw up, which has no reason to be to respect the manifold constraints. So what we do is a tangential projection. So we project dw up onto the tangent plane at point W. And then we choose a retraction operator. So for instance, the exponential mapping will do. And this gives us the next iterate. So basically what this means is that all we have to do to be able to perform the learning with manifold constraints is to know the tangential projector and a retraction. So the exponential mapping, for instance. So we do know them in the Stiefel case and also in the SPD case. So that's it basically. With all these tools, we're able to fully learn an SPD neural network. So we haven't talked yet about second order neural networks, which is the title of the presentation. So now's a good time. So imagine you have some data which is naturally or easily represented or interpreted as the realization of a Gaussian process. You can transform this data using covariance, what we can call covariance pooling, into covariance matrices, and then build an SPD net upon this to do the classification. But in the case you don't have data which is naturally representable as such a Gaussian process, and you still want to use an SPD neural network, that's okay. Because what you can do is use a first-order neural network, so a traditional Euclidean net, so for instance, a convolutional neural network, CNN, and hopefully this first-order model will transform your input data into an output feature space in which now you can interpret the data as the realization of a Gaussian process. So this is what we mean by, or other authors also mean by second-order neural network. It is the appending of an SPD neural network after a first-order standard Euclidean neural network. So it's combining both. So this figure represents this idea. So it's kind of a pipeline. If we have a look at the first line in this pipeline, so here the application is radar data, but the same concept holds for a wide variety of types of data. So if we stay on this first line, we have a simple first-order neural network, which can look like this, for instance. So that's a CNN, pretty standard. Now, if we have a look at the first column, so we have our data. With radar data, it's pretty structured, so we're lucky we can directly interpret it as a Gaussian process. So we do our covariance pooling and then build an SPD net and do the classification. But the interesting part is that you can do this covariance pooling at any step, at any feature representation that you choose most suitable in your first order model. So that means you can go through the layers of your CNN and interpret each output as the representation as a Gaussian process, basically. So you can do this. Here we have a first convolutional FFT layer. So you can do, basically this means we're doing the covariance, we're studying the covariance of the spectrum, but we can also go further in the first order model and interpret any output layer as a Gaussian process, and then build an SPD net upon it. So this particular configuration, if we draw it, looks like this. So it's a pretty big model, and if we code it, it would look something like this, So the class here is SOCNN, so second order convolutional neural network. So we have a first order model, so you can download your favorite CNN from the internet. You have an optional connection here, but then you have the second order model, so we have the bilinear mappings, rectified eigenvalues, etc. You can do what you want. The covariance pooling is down here in the forward pass, a few dense layers. So basically this framework is pretty flexible, and you're pretty free to do as you want. The key idea here is that you can generalize or hope to do better than your standard CNN by appending covariance, second order information into your model. So that's the key idea, really. So how much time do I have left? 5 minutes. So 5 minutes for a few results. So 10? 5 minutes, okay. So so here's a table with numbers, and we won't look too much at the numbers, but I just want to convey a few a few results, conceptually speaking. So it's pretty standard in many fields that it's way simpler to just use the convolutional neural network, a CNN, and we reach state of the art. So in computer vision, in audio classification also, some have tried in BCI. So it's pretty easy to reach really good performance with first order model. So it's this line in the table. So 98 is a good number. I'm not going into the details, but such deep architectures have a tendency to fare pretty badly or poorly in a context with scarce data. So if you take the ImageNet competition data set, lots of data, and CNNs work really well. But if you take 10%, 5% of the training data, you're not guaranteed to reach good performance. On the other hand, using an architecture like SPDNet, which makes use of second order information, you're not necessarily going to reach peak performance with all the data, but you're probably going to be more robust to the lack of data. The idea is that when you're using a neural network which operates on a manifold which is sort of intrinsic, inherent to the data that you're studying, you're introducing a geometric prior into your statistical modeling, and thus you need less data to do the learning. So that's just something I say. It verifies in a few experiments. It doesn't in others, so feel free to try. And another level of interpretation. So the second order neural networks, we recall, combines first order and second order. And actually we can show, so here in just a selected few experiments on radar data in this case, that we're able to make the best of the two worlds. So we're able to reach really good performance, so it's the last line in the table, able to reach really good performance with lots of data, and also remain quite robust to the lack of data when we have not too much data. So that's one key message, which doesn't necessarily translate to other fields, but it's definitely an interesting option. Yeah, so I think I'll conclude my talk here and leave some more time for questions. Thank you.
I'll answer any questions.
So you were talking about using eigenvalue decompositions also during backpropagation, am I right?
Yeah.
Is it quite expensive once the covariance starts to get big? So is it slowing down the process in a strong way, or is it like convenience to still apply techniques?
Yeah, so it depends on many things. So one first answer is that an SPD network has much fewer parameters. So in the experiments we had a CNN with 10,000 parameters, which is quite small for a CNN. The equivalent SPD net had 500, so there's not as many parameters, so that's good. The eigenvalue decomposition is the main bottleneck of this. We use SVD, which is a bit faster and more stable in practice. And for the backward phase, we also just simply save the result of the SVD. We save it for backpropagation, so that reduces the burden. And also the fact that since you're doing a neural network, you're reducing the dimensions at each step. So even if you have a big input matrix, you can reduce it, and then it's not too hungry on resources.
What algorithm did you use to train the weights? So did you use stochastic gradient descent, or what type of?
Yeah, so it's just stochastic gradient descent, but with the manifold constraints and the formulas for the backprop.
With the tangential projector?
Yeah, yeah. So basically, yeah, so you just do SVD, and then instead of updating your weight as you do as usual, you do tangential projection and retraction, yeah.
So you have in your second order networks, you have, if I understood correctly, two networks, a regular one, then the covariance, then the SPD net. Mm-hmm. The first one, is it pre-trained, or do you have an end-to-end training?
Yeah, so it's end-to-end. There's no reason it shouldn't be. It could be it is in practice a good idea to have a pre-trained network. It's not necessary, but it can improve performance, yeah. So basically, yeah, at some point you have Riemannian gradients, then you go through the covariance pooling, which is differentiable. It's just the estimation of a covariance matrix, X transpose, with some modifications perhaps. And yeah, then the gradients just continue.
And do you have an interpretation for the output of this network? Like, did you try to visualize the features it predicts?
Yeah, so you mean the output of the first order?
The first one.
Yeah, so it's just the features that that people use in computer vision. So people interpret them as what's the word? Semantic features.
Yeah. So I mean, when you do the SPD net,
mm-hmm.
after that, and then you have the more robustness, mm-hmm. do you see that the features predicted by the first network actually change, and that they can be useful for something else?
Okay, so you mean if I do the training with the second order neural network, does it improve or change the first one? I do not know. haven't looked at how they change. So.
There was another question. No? I have one actually. So when you use the retraction to do the step in the Riemannian gradient descent, you use the exact exponential, or do you use an approximation? And do you know how it compares in terms of performances?
So I haven't used an approximation, so I don't know how it compares.
Okay.
But I do know that some papers do use an approximation. What I read is about the matrix square root or inverse square root. They use an approximation that uses only matrix multiplications, and it's an iterative process. The interest of this is that you don't need an eigenvalue decomposition, and so you can put this on the GPU and it goes fast. And
you implemented that, the Riemannian stochastic gradient descent, you implemented it yourself, or did you use, there is GOpt, PyManopt, and PyTorch, I believe, that do that and are maybe optimized?
Yes, I'm very aware of their existence. I implemented it. Yeah.
More questions? Okay. You're done?